Okay, section 3.5 is about the equilibrium constant. And when you're at equilibrium, you know that the forward rate equals the reverse rate. So that means if I take the rate equation for the forward and the reverse rate and I set them equal to each other, then I can get something called an equilibrium constant expression. I'm not going to go through the derivation for you. I just need you to understand that the equilibrium constant, which is represented by KEQ, takes the forward and the reverse rates and divides them by each other. And so if I'm looking at a reaction of hydrogen and iodine gases combining to make hydrogen iodide, I would get an expression that looks like this. Now, this comes from taking the concentration of the product raised to the power of its coefficient over the concentration of each reactant. Okay, so if you take a look at the next page, this equilibrium expression takes on the general format that looks like this. So they've taken my products, C and D, divided their concentrations by my reactant concentrations, and whatever the coefficients are in front of each substance, they become the exponents. Okay, so an equilibrium expression is the formula for the equilibrium constant in terms of the concentrations that are present at equilibrium for the reactants and the products. And the equilibrium constant is a number that you obtain by performing the calculation. Now, the units for the equilibrium constant vary. It's something that we're not going to discuss in this class, okay? All right, now, let's take a look at the next page. Okay, in practice problem number 1, we've got some gases at equilibrium in a flask. They give us the concentration of every gas. We've got our hydrogen gas, iodine, and hydrogen iodide. And they want us to calculate the equilibrium constant for this reaction. So the equilibrium constant is equal to the concentration of the products. So hydrogen times iodine divided by the concentration of HI squared, because the coefficient in front of HI is a 2. You simply substitute all of the concentration values in. So this is 4.56 times 10 to the negative 3, and then 7.4 times 10 to the negative 4, divided by 1.35 times 10 to the negative 2, and then you square it. Okay. This comes out to be 0.019, and there is going to be no unit. Easy enough? Yeah? Okay. Why don't you try 2A, and let's see what you come up with. Did you get 11.5? Yes? Okay. We're going to use this to answer 2B. Okay? 2B wants to know whether this reaction is endothermic or exothermic by comparing the equilibrium constant for the reaction at 92 degrees Celsius, which is in the sample problem that was done before these practice problems in the book, and then we compare it with it at 60 degrees Celsius in A, okay? So if you take a look, they gave you the KEQ value at 92 degrees Celsius. It's 4.4. And then the KEQ value that we calculated in part A at a higher temp or at a lower temperature is 11.5. So basically when you drop the temperature, you increase the equilibrium expression, which means you're increasing the equilibrium constant, which means you're increasing the concentration of product. So is this endo or exo? You tell me. Take a guess. Educated guess. Exo. Yep. Because when they dropped the temp, we shifted right. We produced more product. That means the numerator was a greater value. That's why my equilibrium value or my equilibrium constant increased. Does that make sense? Okay. Okay, now you could be asked to solve for an unknown concentration. Do you need me to do one of those examples? It's just where they give you the KEQ value, but you're solving for one of these values. Do you need me to do that, or can you rearrange these equations on your own?
How do we know what's on the numerator and what's on the denominator?
The numerator is the product concentrations. Denominator is the reactant. Okay, can I go on? We got this? Yep. Okay, so then let's take a look at what a bigger equilibrium constant means. So the further we are to the right, the greater the equilibrium constant. Basically, the larger the value, the more we have shifted towards the product. Let's take a look at the next page. You have to be careful with this, and the reason I say you have to be careful is because you can't compare two different reactions and assume, based upon their equilibrium constants, whether one has shifted further to the right or not. Let me give you an example. Here are two different reactions here, but they both have equilibrium constant values of 1. Can't compare them. If it was the same reaction and we were maybe at different temperatures, no problem, okay? But you can't do that in this case. You also can't deduce what like position you might be at. So up here it says it's impossible to infer anything about the equilibrium position based upon the equilibrium constant alone. So the equilibrium position depends upon what were your concentrations when you initially started and what's the equilibrium constant value. Okay, so here if I'm looking at this reaction, which has this equilibrium constant value, if my initial concentration of my reactant was 1 molar, your percent yield is only 0.42% when you're at equilibrium. But if the initial concentration is 1 times 10 to the negative 6 molar, guess what? You have a 95% yield. Okay, so that's just something to consider. When you're looking down here at what you can do to change the equilibrium constant, changing the temperature is the only way to change the equilibrium constant value, and that is observed in the table at the bottom of the page. So down here you will notice that they added reactant, they changed the volume, and then they changed the temperature. The only one that changed the equilibrium constant was the temperature. Okay, take a look at the next page. Let's do the quick check. If you add ammonia to this reaction, what direction will we shift? Anytime you add something, you shift away from it. Okay, so we'll shift right. Will this affect the equilibrium constant? Think carefully about that. No, why not? What will affect the equilibrium constant?
Only temperature.
Only temperature. Number 2, we're going to decrease the temperature of this reaction. In which direction will I shift? This is endo, right? If I take heat away from a reaction that needs it, which direction will we shift? Anytime you take away something, you move towards it.
Left.
Okay. What will happen to the percent yield?
Decreases.
Decreases. What happens to the equilibrium constant?
Goes up.
It goes where? If I decrease the temperature. Aren't I decreasing the concentration of product? Because I shift left. So my equilibrium constant has to go down. Number 3, consider the following. True or false? We know that reactants are favored in this reaction because your equilibrium constant is less than 1. It's false. Let's talk about liquids and solids. Liquids and solids are never included in equilibrium expressions. So if you take a look down here, if I were to write the equilibrium expression for the equilibrium that forms when sodium chloride dissolves and produces its ions and then it recrystallizes, your equilibrium expression will not include the solid. Okay? Let's take a look at another example. Let's come down here. Which of the substances in this reaction are not included in my equilibrium expression? Water. Yeah, because water is a liquid. So liquids and solids not included in an equilibrium expression. Let's go to the next page. And number 1, which would be omitted from the equilibrium expression?
B2 of 3.
Yep, this one. So that means your equilibrium expression would be H2O in brackets raised to the 3rd power over B2H6 times O2 raised to the 3rd power. Right? Product concentration over reactant concentration. And whatever the coefficients are, those become the exponents. In number 2, there isn't anything I would exclude. Okay, because I don't have any solids or liquids. In number 3, exclude the liquid. In number 4, exclude the solid, right? So that way in number 4, this would simply be the calcium ion concentration times the carbonate ion concentration. Okay? Yeah.
If you're excluding everything in the products, would it be
1 over? Yeah. Okay, now let's talk about what happens to KEQ if I reverse a reaction or I multiply a reaction by a whole number or I divide it by a whole number. So here we've got, I better stop this, hold on.